The F-35 was built to dominate for decades. By early 2025, more than 1,100 have been delivered across the globe, with program goals aiming for roughly 3,500 over its lifetime. The fleet has already logged over 1 million flight hours, underscoring its scale. Yet while other top defense contractors shift towards sixth-generation designs with AI copilots and adaptive engines, Lockheed Martin finds itself absent from America's official next-gen programs. Instead, its leadership proposes a Super Lightning upgrade, claiming it could deliver much of sixth-gen performance at far lower cost. Whether that pitch secures its future is another matter. From fleet leader to question mark. By early 2025, the F-35 stands as the core of Western air power. Operated in 3 variants by the US Air Force, Navy, and Marine Corps, it anchors a network of allied fleets stretching from the Arctic to the South Pacific. About 1,100 plus have been delivered worldwide, and Lockheed Martin reports the fleet has surpassed 1 million cumulative flight hours. More than 15 nations fly it in roles ranging from frontline interception to deep strike, and as network command hubs linking 4th and 5th generation assets. In scale and availability, no rival stealth fighter force comes close. That reach is more than a statistic. In 2025, Israel's F-35I jets reportedly executed deep strike missions against targets across the region, leveraging their stealth and standoff weaponry. In Europe, US and allied F-35s regularly conduct NATO air policing and intercept operations from Iceland to the Baltic, projecting a visible deterrent in contested airspace. Exercises across multiple theaters now integrate F-35 squadrons into complex simulated battles, with the jets feeding sensor data to allied aircraft and ground networks in real time. Interoperability has been central to the program's appeal. Nation-specific weapons and software adaptations exist, but all operators share a common platform capable of advanced data fusion and secure communications. Joint training has smoothed differences in tactics and procedures among partner air forces. For many countries, the F-35 isn't just another aircraft. It is the operating system for coalition-wide air combat. That said, production has not been entirely without disruption. While manufacturing has been steady over the long term, the rollout of the Tech Refresh 3, TR3, hardware and software upgrade caused a temporary delivery hold. A backlog of finished aircraft went into storage awaiting software readiness, and deliveries resumed only under an interim configuration, pending future updates. It was a reminder that keeping such an advanced platform on schedule and combat ready depends as much on software integration as on airframe assembly. The original vision for the F-35 anticipated decades of uncontested dominance among 5th-generation designs. Hundreds more aircraft are on order, and assembly lines are booked years in advance. Yet defense ministries are increasingly weighing whether resources should shift towards 6th-generation fighters rather than expand F-35 fleets indefinitely. This isn't just long-term force planning. It is an active debate shaping procurement decisions today. In the United States, the Air Force's Next Generation Air Dominance Program and the Navy's F/A-Roman-20 initiative are pushing ahead without Lockheed Martin in the lead role. These efforts aim to deliver sensor ranges, weapons integration, and adaptive propulsion systems beyond the F-35's designed envelope. Being absent from that leadership tier means more than missing contracts. It can influence perceptions about which companies will define the next era of air combat. Abroad, key allies are pursuing their own advanced fighter programs. The UK, Italy, and Japan are jointly developing the Global Combat Air Program. France, Germany, and Spain are moving forward with the Future Combat Air System. Both aim to leapfrog current generation capabilities and secure a technological edge over rival powers. Lockheed Martin, for all its dominance in fielded stealth fighters, is not central to these multinational 6th-generation projects. This leaves the F-35 in a dual position, unmatched in operational presence, yet exposed to strategic obsolescence pressures. Advances in radar sensitivity, passive detection, electronic warfare, and unmanned teaming threaten to erode many of the advantages stealth fighters enjoy today. The pace of change is accelerating, making it possible for even highly capable platforms to be outclassed faster than in previous generations. Within the US, the question is one of balance. Should funds and engineering talent focus on stretching the F-35's capabilities further, or migrate toward aircraft designed without the constraints of earlier designs? Service branches have already committed to all new flagships in their upcoming fleets, signaling a willingness to move beyond the current baseline. For Lockheed Martin, that raises the stakes on keeping its signature fighter relevant through major evolution rather than incremental tuning. It is a precarious balance. The F-35's large installed base is a major advantage. Replacing it wholesale before the end of its planned service life would be logistically and financially difficult for every stakeholder involved. At the same time, adversary forces are expected to introduce improved counter-stealth technologies, better sensor fusion, and high-volume drone support operations, all designed to challenge fighters like the F-35 from multiple angles. Sunk costs offer no protection against those rising threats. Recognizing this, Lockheed has sought to position the F-35 not as a static legacy platform, but as a continuously modernized system. This is where the proposed advanced variant concept gains strategic weight, not as a marginal update, but as proof that the current airframe still has room for significant capability growth. For operators, the calculus will vary. Some air forces will want every available upgrade at the earliest opportunity, while others will prioritize cost control and compatibility with their existing jets. Any enhanced version must deliver performance gains large enough to warrant adoption without pricing out the allies who form the core of the program's global reach. Today, the program sits at a crossroads between two contrasting narratives. In one, the F-35 remains the indispensable cornerstone of allied air combat for years to come. In the other, exclusion from leading sixth-generation projects marks the start of a time-limited dominance, with its technological overmatch gradually eroding. Ensuring that the first storyline continues to define the aircraft requires demonstrating that what's flying now is still among the most advanced fighter capabilities available anywhere. That reality is what sets the stage for assessing the aircraft as it exists today, before considering how far it could still evolve. What the current F-35 really offers. In 2025, most newly fielded F-35s align with what's often called the Block 4 configuration. Externally, the jet still matches the familiar profile, a single-engine, single-seat stealth fighter capable of about Mach 1.6, powered by the Pratt & Whitney F-135, producing over 40,000 pounds of thrust with afterburner. Combat radius remains around 670 nautical miles on internal fuel, and it can stay transonic while carrying weapons internally, preserving its low observability. The fundamentals are consistent, but under the skin, the differences matter more than the silhouette. Many recent airframes have been built with the new Tech Refresh 3 TR3 hardware, a computing backbone meant to unlock Block 4 expanded capabilities. However, the TR3 software rollout ran into delays and stability issues, with test pilots noting occasional mid-flight system resets during early trials. These problems triggered a halt in deliveries through much of 2023. Production continued, but completed jets were stored until deliveries resumed in phases, first with a stripped-down interim software load in 2024, and then with incremental updates into 2025. This staged approach means that even among Block 4 capable aircraft, not all features are live yet across the fleet. When functioning as intended, Block 4 brings three core combat advantages: more powerful computing to process and share far greater volumes of sensor data, integration of new and longer-range weapons, and upgrades to electronic warfare and targeting systems. Its AP81 radar works alongside improved electro-optical targeting, the distributed aperture system, and updated radar warning receivers, giving pilots a wide and fused view of the battle space. Over time, certain U.S. aircraft are planned to receive the F-35 active electronically scanned array radar, which promises higher resolution tracking and greater resistance to jamming. Though this sensor leap is still in the development and integration phase rather than in operational service. Stealth remains central to how the aircraft fights. From the front and side aspects, its radar cross-section is comparable to a small object, ensuring that older fighter radars have trouble detecting it early. Design features like edge-aligned surfaces, an S-duct inlet masking the engine face, and exhaust treatments help suppress radar and infrared signatures. For missions aimed at advanced surface-to-air missile networks, these characteristics still allow entry where non-stealth aircraft must operate from standoff range. Real-world operations between 2022 and 2025 have shown what this means. U.S. Marine Corps F-35Bs from amphibious ships in the Pacific have simulated strikes into defended island chains, using targeting data from unmanned scouts and relaying those to surface vessels for follow-on missile shots. Over the Baltics, U.S. Air Force and Royal Air Force F-35 as on patrol have shadowed foreign aircraft while remaining electronically silent, tracking via passive sensors. In the Middle East, Israeli F-35s have reportedly penetrated defended airspace to hit radar sites, relying on stealth and onboard electronic warfare to avoid engagement. Exercises have been equally revealing. In a 2023 U.S. Air Force scenario simulating a denied A2AD environment, Block 4-equipped F-35 used their fused sensor picture to lead coordinated, multi-axis strikes with allied fourth-generation fighters. Pilots could prioritize high-value targets amid decoys and heavy jamming, compressing engagement timelines. In another test, U.S. Navy F-35CS integrated with carrier defenses to detect and intercept low-flying cruise missile surrogates before they reached the fleet. This flexibility underpins why the jet is still prized. It's not only a shooter, it's an airborne command and sensing hub, able to feed targeting data to other aircraft and ground forces in real time. Weapons loadouts add to that adaptability. Internally, it can carry combinations of air-to-air missiles and precision bombs while retaining low signature. When stealth is less critical, external pylons boost payload. Block 4 widens the menu, bringing newer GPS and laser-guided bombs, enhanced anti-ship missiles, and expanded electronic attack options. Pilot interface remains a distinct strength. The helmet-mounted display replaces conventional gauges with projected symbology, video feeds, and targeting information, all integrated by Block 4 faster processors. More of the incoming sensor data becomes useful without overloading the pilot in combat. Even in its current form, the design is meant to absorb changes. Components, hardware and software are modular to allow upgrades without replacing the aircraft outright. This was deliberate to keep the airframe viable through mid-century. For propulsion, there's been discussion of adaptive cycle engines from the Air Force's AETP program. Prototypes have flown, but fitting them across the fleet proved politically and logistically complex, leading the Joint Program Office to focus instead on an F-135 engine core upgrade to deliver needed performance and thermal margins without a complete re-engining. Survivability in practice is more than low detectability. Block 4 enhanced electronic warfare features can automatically jam or deceive radars and missile seekers once they lock on, buying time for the pilot to evade or finish the mission. Against modern, multi-band SAM systems, these automated defenses can be decisive. From 2022 to 2025, the fleet's record suggests the current F-35 remains highly capable against advanced air defenses. The combination of stealth, sensors, and network targeting keeps it relevant even as counter-stealth measures evolve. That solid baseline is why discussions about upgrades focus on building further rather than replacing the architecture outright. Initiatives such as the proposed Super Lightning are framed as evolutionary steps, bringing in capabilities like autonomous drone teaming, improved coatings, and engine or cooling enhancements. These are ideas often associated with aircraft still on the drawing board for the next generation, but many of them could in theory be folded into the F-35 structure without eroding its core advantages. The relevant debate is no longer about whether the Block 4 standard can fight. It has proven it can. But about how long that edge can be sustained in the face of changing adversary technology. That question is growing sharper as rival programs aim to leap beyond today's capabilities entirely, with timelines converging in the coming decade. The sixth generation disruption. In the United States, sixth-generation combat aviation has shifted from theory to funded programs with defined timelines. The Air Force's next-generation air dominance effort, a deliberate system of systems approach, is now in active development. At its center is a Boeing-led manned fighter, often referred to in defense circles as the F-47, with surrounding families of supporting systems, autonomous drones, advanced sensor networks, and resilient battlefield communications. While program goals include technologies such as adaptive cycle engines for greater range and performance, integrated AI copilots to manage data and coordinate unmanned teammates, and spectrum-wide signature control, these remain targets rather than operational realities. The Navy's Parallel F/ a Roman 20 program follows the same philosophy, but is purpose-built for carrier use, prioritizing unrefueled reach for operations in the Pacific, flexible payload options, and maritime hardened systems. Both services aim to leap beyond the incremental upgrade model that defined prior generations. The concepts start with stealth as only one layer in a broader survivability package, integrating distributed and passive sensors throughout the airframe and interconnected systems. Networked in real time, these aircraft are envisioned to serve simultaneously as strike platforms, reconnaissance nodes, and battle managers. AI decision aids could reduce pilot cognitive load, enabling manned crews to orchestrate multiple unmanned assets in contested environments without losing situational awareness. Among the most potentially disruptive elements are loyal wingman drones, autonomous or semi-autonomous aircraft equipped for sensing, jamming, decoy, or strike missions. They would operate in concert with manned fighters, probing defenses or engaging targets while keeping human pilots out of the most dangerous positions. Program objectives call for seamless in-flight retasking of manned-unmanned formations, allowing strike packages to adapt quickly to changing threats. Abroad, allied governments are advancing parallel sixth-generation plans. The Global Combat Air Program, led by the United Kingdom in partnership with Italy and Japan, aims for the mid-2030 with an emphasis on sensor fusion, advanced propulsion studies, and human-machine teaming competitive with US developments. On the continent, the France-Germany-Spain Future Combat Air System targets a similar in-service window, built around a combat cloud, linking a next-generation fighter to drones, satellites, and ground networks. Both mirror the US approach of pairing an advanced crewed platform with autonomous systems under a shared digital battle space, adding pressure on timelines and reinforcing the shift in force design. China and Russia are also pursuing their own paths toward post-fifth-generation capabilities. Public information is limited, but reporting suggests Chinese research into adaptive propulsion, multi-domain networking, and pilot drone teaming, while Russian work appears more focused on affordability and integrating hypersonic strike into stealth platforms. Even if these efforts trail the US or its closest allies in certain technologies, their existence accelerates the imperative for sixth-gen readiness in Western planning. For Lockheed Martin, the change in procurement landscape carries strategic weight. Despite decades of dominance in the fifth-generation market through the F-35, and its experience with the F-22, it is not the prime contractor for either the Air Force's NGAD manned fighter or the Navy's F/ a Roman 20. That means the centerpiece aircraft in each service's future frontline mix will be designed and built without Lockheed in the lead role. The prime-level contractors will set architecture choices, shape sustainment models, and lock in proprietary frameworks that could define air combat for a generation. Lockheed remains engaged in advanced research, holds intellectual property from its NGAD bid, and maintains development capacity in key technologies such as avionics, sensors, and mission systems. According to CEO Jim Taiclet's public statements, elements from its NGAD design work can be adapted for use on existing platforms, including the F-35 and even the F-22 where relevant. Yet the absence from prime status in the US manned 6th generation programs changes its degree of influence. Subsystem supply contracts sustain a technical presence, but they do not offer the same leverage over future upgrade schemes or overarching combat doctrine. For current F-35 operators, the emergence of these new aircraft ecosystems brings practical considerations. 6th generation fighters are likely to employ different software environments, logistics networks, and maintenance training regimes. Moving from an F-35-centric fleet to a force anchored by a 6th gen system could involve parallel supply chains for years, with associated costs and complexity. Each Air Force will have to weigh the potential capability advantage against the disruption and expense of introducing a fundamentally new design. The operational ambitions of 6th generation concepts go beyond higher speed or stealthier profiles. Adaptive engines aim to shift in flight between efficient cruise and high-thrust combat modes, potentially extending range by a quarter over today's stealth jets. AI support crews promise to filter and act on the torrent of sensor data that would overwhelm a single pilot, particularly in dense electronic warfare conditions. Distributed sensing means a formation can detect, track, and target threats without emitting from its own radar, reducing exposure to adversary detection. Loyal wingmen expand offensive and defensive options without adding more manned cockpits to the order of battle. Combined, these targeted advantages could make it difficult for even upgraded 5th generation aircraft to match the operational flexibility of clean sheet 6th generation designs. Airframes constrained by original assumptions, single crew workload, certain aspect-dependent stealth shaping, fixed propulsion, can integrate new tools, but rarely as deeply or efficiently as a platform conceived with them from inception. This gap is why procurement planners often earmark entirely new designs for leaps in capability, rather than relying exclusively on legacy platform development. For Lockheed Martin, the structural challenge is clear. Their F-35's production line and global sustainment network ensure its presence into mid-century, but leadership in defining the next era belongs to those shaping the first operational 6th generation fleets. Without a prime role in NGAD or F/Roman 20, Lockheed must look for other ways to influence and participate in that future battle space. The company's approach, publicly signaled in recent years, has been to reframe its flagship fighter not as a legacy design frozen in time, but as a platform with headroom for major capability growth. Advanced avionics from future programs, next-generation weapon integration, improved thermal management from adaptive engine research, and manned-unmanned teaming concepts could, in theory, be adapted to the F-35's architecture. If those capabilities can be brought to service quickly and affordably, the argument follows that the gap to 6th generation designs could be narrowed enough to preserve relevance. This is the competitive environment in which new proposals are taking shape. For Lockheed, maintaining its position in the world's most capable air forces now depends on translating its research and design investments into upgrades that matter to current operators, and doing so before the 6th generation fleets arrive in numbers. Conception of the Super Lightning. Lockheed Martin's Super Lightning concept emerged not from a formal Pentagon program, but from a deliberate internal pivot. The trigger came in early 2025, when CEO Jim Taiclet told investors during the April quarterly call that the company intended to apply technologies developed for its next-generation air dominance and other 6th-generation bids to existing F-35 and F-22 platforms. He set a clear challenge for his engineers: deliver roughly 80% of the capability jump expected from sixth-generation designs, but at around half the cost. It was Lockheed's own strategic pitch, not an endorsement from the US Air Force, aimed at turning stranded research and development into a marketable advantage. The thinking was straightforward. Losing prime contractor status on NGAD and the Navy's F/A Roman 20 had left Lockheed with advanced concepts, prototypes, and subsystem test data that were no longer tied to a funded fighter program. Scrapping that investment outright would mean writing off years of R&D, folding those technologies into the already proven F-35 airframe offered a way to monetize them, while keeping the company in the conversation about cutting-edge combat capability. Inside the company, the Super Lightning idea drew on work already done for clean-sheet sixth-generation proposals, conceptual designs, wind tunnel evaluations, and component prototypes. These included improved low-observable coatings with better durability and multi-band performance, autonomy and AI-driven mission systems for threat assessment and route planning, manned-unmanned teaming frameworks, advanced sensor and data fusion packages with expanded processing throughput, and compatibility provisions for upcoming long-range and multi-mode weapons. While originally conceived for new aircraft architectures, engineering teams assessed that these elements could be adapted to the F-35 with targeted structural modifications and systems integration. The appeal to customers was clear. An F-35 enhanced with this technology suite could be positioned as an evolution, not a replacement. Existing F-35 operators, now numbering in the thousands, had already invested heavily in pilot training, maintenance pipelines, simulator infrastructure, and spare parts stocking. Keeping those investments relevant, while gaining much of the intended operational impact of a sixth-generation fighter, would avoid the cost and disruption of introducing an entirely new airframe. Lockheed's internal projections avoided headline comparisons on raw speed or pristine stealth from every angle. Instead, engineers concentrated on the attributes that most influence combat outcomes in realistic scenarios: reduced detectability by emerging sensor networks, computing power to process and exploit growing volumes of sensor data, expanded engagement envelopes for both air-to-air and strike weapons, and partial automation to help a single pilot manage complex, multi-asset missions. Performance gains of that kind could deliver tangible tactical advantages, even without matching every technical specification of a purpose-built sixth-gen jet. Strategically, the Super Lightning offered answers on several fronts. To long-term F-35 customers, it suggested a route to remain competitive without waiting for the 2030s. For Lockheed, it kept advanced fighter manufacturing and integration skills engaged and profitable. For governments, it provided an option that could be bought in quantity and brought into service sooner, sidestepping some of the cost and schedule risks that come with scaling up an all-new type. Technical transfer candidates from NGAD work were prioritized according to impact and integration cost. Stealth refinements for the rear aspect of the aircraft targeted vulnerabilities against modern, full-sphere radar systems. Mission computers designed for AI-assisted control of unmanned teammates could be swapped into existing avionics bays, enabling advanced coordination functions. Onboard AI copilots, software agents capable of monitoring the battle space, correlating sensor tracks, and recommending courses of action, could be layered into pilot workflows without wholesale redesign of the cockpit. New weapon interfaces could bring in evolved missile types able to engage multiple target classes with adjustable seeker modes. Even defensive technologies, such as compact, directed energy countermeasures, first explored for use on autonomous escorts, were considered for adaptation. From a sales perspective, this hybrid approach played to practical procurement realities. Many allied air forces were under budget constraints, juggling investment in drones, missile defenses, and cyber capabilities alongside their fighter fleets. extending the relevance of existing jets at manageable cost was likely to resonate more than committing to an unproven design with a long delivery horizon. There was also a geopolitical logic. Access to US sixth-generation aircraft will not be universal. As with past fighter programs, export versions are expected to carry performance restrictions. A Super Lightning upgrade path could serve as the top-tier exportable option, offering much of the operational benefit without breaching sensitive technology controls. This would reinforce Lockheed's role as a key partner, keeping allied forces aligned with US operational methods and sustainment systems. Timeline pressures reinforce the business case. Operational sixth-generation fighters in the US inventory are not expected in mass numbers until well into the next decade. Adversary capabilities, especially in integrated air defenses and sensor fusion, will continue to advance in the meantime. A fielded Super Lightning variant could narrow the performance gap quickly, complicating any attempt to exploit a window before sixth-gen fleets mature. Lockheed has been candid that this is a trade-off. Even with substantial upgrades, a re-engineered F-35 will not replicate every advantage a new generation fighter can deliver. Airframe shaping constraints, propulsion integration limits, and baseline systems architecture all set boundaries. But the company's public argument is that the capability versus cost balance will still favor this evolutionary approach for many operators until sixth-generation affordability and availability improve. Framed this way, the Super Lightning is less a side project than a deliberate realignment of resources and ambition. It represents an attempt to recast the F-35 not as yesterday's platform, but as a foundation robust enough to absorb key advances from the next era of air combat. The substance of that transformation rests in specific hardware and systems changes now being evaluated, alterations intended to close those most exploitable gaps against future threats, while preserving the strength that made the jet valuable in the first place. From the cockpit outward, these proposals begin with the areas most visible to an adversary's sensors. Proposed airframe and stealth enhancements. Lockheed Martin's plans for the Super Lightning start with physical changes the company claims could reduce the aircraft's detectability across a broader range of viewing angles. One of the headline priorities is lowering its rear aspect radar signature. The baseline F-35 was shaped primarily to defeat frontal and side radar threats typical of the early 2000s, assuming radar sites or interceptors would try to spot it head-on before it launched weapons. Current integrated air defense networks use distributed radar nodes and passive sensors positioned to cover multiple sectors. When a stealth aircraft passes those sites, the heated exhaust area and aft fuselage become far more visible. Lockheed's engineers have identified reshaping aft fuselage edges, tail boom contours, and the surfaces around the nozzle as possible ways to scatter or deflect radar returns in that hemisphere. These remain design studies, not fielded modifications, and company officials acknowledge that rear aspect shaping will be carefully balanced against cost and aerodynamic trade-offs. Infrared signature control is tied closely to that radar work. Modern infrared search and track systems on fighters, ground stations, and even large surface ships can detect an engine heat plume well before visual contact. In the Super Lightning concept, cooling approaches adapted from Lockheed's sixth-generation R&D are under review for the rear section. Ideas include modified nozzle shrouds, ceramic heat shielding designed to spread and cool exhaust flow, and active airflow channels to mix ambient air with hot gases before release. Each is intended to reduce the intensity and concentration of the heat plume during high-thrust phases. If adopted, this would complicate targeting by advanced imaging infrared sensors, though the company notes any such integration would have to pass performance, weight, and maintenance assessments first. The proposal also includes adjustments to existing inlet and outlet designs. The current S-duct inlets block a direct radar line of sight to the compressor face, but testing has shown angles and frequencies where returns still occur. Lockheed studies look at slightly altering inlet lip geometries, incorporating sharper edge treatments, and layering more radar-absorbent material along internal surfaces to further attenuate unwanted reflections. Exhaust nozzle edges could be given serrated or reprofiled contours to scatter radar energy, especially for low-frequency systems looking down the tailpipe. Lockheed frames these as refinements that could be added during production or major overhauls, distinct from wholesale redesigns, which would approach creating a new aircraft with higher cost and schedule risk. Upgrades to radar-absorbent coatings are also part of the package. The F-35's original coatings were optimized for the radar bands most common on threat systems during its design phase. In the past decade, adversary sensors have expanded into both lower-frequency surveillance bands and higher-frequency targeting sets to bypass so-called frequency-tuned stealth shaping. Lockheed says its newer coating formulations broaden the absorption range into challenging L-band and low OOF spectrums, while also improving resilience to weathering and abrasion. That matters because stealth sustainment is already a known issue. US test and operational reports have flagged the labor-intensive process of repairing and reapplying coatings as a persistent burden. Introducing more complex geometries or advanced materials could improve survivability, but also make upkeep harder, an operational trade-off any customer would need to weigh. Lockheed's emphasis on rear aspect and low-frequency protection reflects changes in the threat environment. Multi-static radar arrays can network dozens of smaller emitters over large areas, pooling their returns to detect aircraft from angles assumed safe in the past. In such conditions, reducing the chance of a successful rear aspect track is more than a niche gain. It becomes necessary for any deep penetration mission. Above and around those networks, high-altitude surveillance aircraft and space-based platforms bring downward-looking radar and infrared systems into play. Here, aft body recontouring, reshaped edges, and diffused exhaust flow could help break up the symmetry of a contrail or heat trail, delaying a positive fix. The company stresses the modular nature of the F-35 design as a facilitator for these changes. Most exterior shape adjustments under consideration do not require rearranging internal fuel or systems, making them compatible with both new builds and major depot visits. Coating upgrades could be applied during routine surface maintenance, and inlet or exhaust changes incorporated into engine servicing cycles. That update path is central to Lockheed's sales argument, closing part of the stealth gap to sixth-generation designs without waiting on a costly clean sheet program. Not all airframe changes under discussion are aimed at detection reduction. Range extension is another operational goal, and some operators are already experimenting with solutions. Israel's work on conformal fuel tanks and external drop tanks for its F-35 aims to provide longer reach in scenarios where low observability is less critical, such as transiting friendly airspace or during egress after weapons release. These modifications illustrate the trade-off inherent in any airframe addition. More fuel extends range, but increases signature, so their use must be tailored to mission type and threat environment. For the Super Lightning, Lockheed could build on such precedents to offer optional range packs that integrate with the proposed shaping and coating changes. Engineering all these enhancements demands careful performance trade-off analysis. Measures that cut infrared output can sometimes add drag or constrict engine airflow, impacting acceleration and range. Lockheed's development studies use computational fluid dynamics to evaluate dozens of aft body and nozzle variations, looking for combinations where signature reduction outweighs performance loss. The company's position is that the right mix can extend the jet's survivability without compromising its multi-mission flexibility. Operationally, improved rear aspect stealth has clear effects in dense threat regions. In the Pacific, where sensor sites can be spread across island chains, an egress route may still take a strike aircraft past hostile coverage. Reducing detectability here could prevent an enemy from vectoring interceptors or tracking the aircraft to vulnerable en route points like a tanker. In European airspace, low-frequency radars and infrared detection grids reach across borders. A higher detection threshold forces an adversary to rely on its most advanced assets or accept gaps in tracking coverage, complicating their response and buying time for friendly forces. In Lockheed's framing, the combined effect of shaping tweaks, exhaust treatments, and expanded band coatings would not transform the F-35 into a sixth-generation jet, but would slow the erosion of its edge. By addressing radar and infrared vulnerabilities from more angles and frequencies, the Super Lightning package is meant to extend the period in which the aircraft can enter defended airspace, complete a mission, and exit without early interception. That survivability interval is the value proposition, keeping the fifth-generation platform viable while the next wave of fighters is still in limited service. These structural and signature management studies form the foundation of the Super Lightning's external upgrades. From here, Lockheed's concept turns inward, examining changes in how the aircraft thinks, senses, and fights, areas where advances in computing and control could shift its role well beyond what its current cockpit and systems were designed to do. AI integration and autonomy. Lockheed Martin presents autonomy as one of the most transformative capabilities under its Super Lightning proposal. The company's public comments, including CEO Jim Taiclet's recent statements, frame this as a short to mid-term corporate goal, an F-35 variant that is pilot optional and equipped with an advanced AIcopilot. In their concept, the aircraft could be flown conventionally with a human pilot or operated in semi-autonomous and, under certain conditions, fully autonomous modes. This is not fielded reality, but a planned capability the company claims could allow the same squadron to assign one jet to a manned strike, another to an uncrewed reconnaissance sortie, and a third as a command node for unmanned escorts. Central to that vision is the AIcopilot. Rather than a more capable autopilot, this is described as an onboard mission manager that can process and fuse radar, infrared, electronic and visual data, identify and prioritize threats, cue weapons, and recommend maneuvers. In theory, during combat, could autonomously adjust routing and timing to minimize exposure or automatically trigger defensive countermeasures if an incoming missile is detected. In lower threat environments, the same system might coordinate distributed surveillance tasks among multiple aircraft without adding to the pilot's cognitive load. In crewed operations, Lockheed's planning documents indicate that this AI layer is intended to reduce workload and simplify decision-making. Current multi-role fighter pilots balance a dense mix of radar tracks, targeting pod feeds, infrared search detections, communications, and navigation. The proposed AI would sort, filter, and present only the highest priority information to the pilot's helmet display and controls, allowing focus on mission execution. Automated handling of certain defensive responses, like jamming or decoy deployment, would buy seconds that can determine survival in high-speed engagements. A major element of the proposal is manned-unmanned teaming. In Lockheed's scenario, a Super Lightning could control several unmanned combat air vehicles, directing them to serve as decoys, extend the formation's sensor reach, or attack specific targets. These autonomous escorts might be lower cost and semi-expendable, assigned to missions too dangerous for a manned jet. The AIcopilot would dynamically allocate tasks, sending one drone to suppress a newly detected surface-to-air missile site, while another pushes forward to locate mobile launchers beyond the lead jet's own sensor horizon. Here, the idea builds on more than paper studies. Lockheed Martin has already participated in successful US military demonstrations where manned fighters, including F-35s in certain trials, have controlled multiple unmanned aircraft in coordinated maneuvers. These tests, often in partnership with the Air Force Research Laboratory and Navy development programs, prove that existing F-35 data links and mission systems can provide real-time tasking to two or more autonomous drones. The Super Lightning program positions its autonomy features as an extension of those demonstrated capabilities, scaling up processing power, refining AI algorithms, and integrating more sophisticated levels of control. Realizing these ambitions will require significant technical work. Proposed AI and autonomy functions depend on secure, jam-resistant communications to keep a link between the lead aircraft, its drones, and command networks. That means advances in encryption, frequency-hopping waveforms, and the ability to route control commands through multiple redundant paths, satellites, airborne gateways, and line-of-sight radio. A cut link in combat could render an autonomous escort useless or unpredictable, so keeping connections resilient is a central engineering priority. There are also regulatory and certification issues. Trusting a multi-million-dollar combat aircraft to an AI system, particularly in armed roles, raises operational and political questions. Airworthiness and safety regulators will want extensive testing to validate that autonomy does not increase collision risk or cause unintended engagements. Rules of engagement will have to address how much lethal authority can be delegated to a machine, if at all, in complex, politically sensitive environments. Because export variants of the F-35 are already subject to technical restrictions, full autonomy packages may not be cleared for all foreign operators, limiting how widely the most advanced modes can be offered. Lockheed suggests a phased rollout to address both technical and political hurdles. Semi-autonomous assistance could arrive first, AI that manages sensors, navigation through GPS-denied zones, or defensive countermeasures, while leaving flight control and weapons released to a human pilot. As confidence grows and communications reliability improves, more functions could be shifted to automation. Fully uncrewed missions, such as high-risk reconnaissance over well-defended areas, would likely be among the last to see clearance, deployed selectively where loss of the jet would be strategically acceptable. The proposed software and processing upgrades are intended to be modular, allowing retrofit to existing airframes with minimal structural change. A nation could buy into the autonomy package by installing new mission computers and loading updated software, avoiding the procurement cost of new aircraft. The approach also lets operators choose the extent of AI they adopt. Those wary of security or political implications could stop at enhanced sensor fusion and pilot assist features. Others could progress toward active control of unmanned wingmen. If implemented, these capabilities would expand the F-35's role well beyond its original strike fighter remit. An AI-enabled Super Lightning could act as a forward battle manager, taking in data from satellites, airborne early warning aircraft, other fighters and drones, then assigning targets or reconnaissance tasks in real time. Bringing this decision-making to the edge of the fight reduces dependence on centralized controllers who might be saturated in a high-intensity conflict. From an operational standpoint, even partial autonomy could change mission design. For example, a pilot focused solely on air-to-air battles could hand suppression of enemy air defenses to AI-controlled escorts. In maritime strike, the lead aircraft could direct its drone teammates to reconnoiter ahead, identify targets, and execute concurrent attacks, compressing timelines and saturating defenses. For air forces with limited pilot pools, shifting some missions to uncrewed mode could maintain sortie rates without equivalent investments in training new aviators. Lockheed's timeline for such integration is aligned with available technology. With AI processors, open architecture software frameworks, and manned-unmanned control protocols already tested in other programs, the company argues that a first-generation AIcopilot could be fielded within this decade. Achieving resilience, trust, and exportable versions will take longer, but the groundwork is present now. By framing autonomy as a scalable upgrade, Lockheed is positioning the Super Lightning as more than an iterative stealth fighter. In their pitch, it could become a flexible asset, sometimes a crewed strike platform, sometimes an uncrewed reconnaissance node, sometimes the centerpiece directing an autonomous formation in contested airspace. As with the proposed shaping enhancements, the aim is to close capability gaps forming against emerging threats without waiting for entirely new aircraft programs to mature. To make such a role credible, however, autonomy has to work hand in hand with systems that can identify, track, and engage threats far faster and farther than the current standard. That places the next focus squarely on the sensors and weapons the Super Lightning might carry, and how those tools would expand what the aircraft can do once its AI decides where to act. Weapon systems and sensor overhaul. For the Super Lightning, Lockheed's weapons roadmap is framed around adapting to future threat environments rather than simply adding more payload. On the defensive side, one avenue under study is the integration of a scaled directed energy weapon for short to medium range protection. This remains an experimental concept in Lockheed's research portfolio, not a near-term fit for operational aircraft. The idea is that a compact high-energy laser could be used to disable or destroy incoming missiles, drones, or slow-moving aircraft within visual range. Key hurdles include generating enough power and managing heat in an airframe not designed from the outset for such demands. Internal engineering reviews have examined whether uprated generators and dedicated cooling loops could be added without compromising range or stealth. If eventually feasible, the payoff would be a defense layer immune to ammunition limits, but the company is careful to present this as a possible long-term capability rather than an imminent upgrade. Offensively, Lockheed points to developments already underway that could expand the Super Lightning's reach and lethality. In March 2025, the company announced an F-35 flight test of the Long-Range Anti-Ship Missile, LISM, confirming the jet's ability to deliver standoff strikes against naval targets at extended ranges. In the air-to-air arena, testing of the AIM-260 Joint Advanced Tactical Missile continues, with the aim of surpassing the range of current AMRAAMs and preserving engagement dominance against peer fighters. These examples show how the Super Lightning's weapon set could incorporate proven or maturing systems while retaining the flexibility to integrate future designs. The upgrade plan also looks at very long-range precision strike for land targets. Air-launched cruise missiles with ranges in the hundreds of miles could allow the aircraft to conduct deep strikes from outside dense air defense zones. Compact, stand-in munitions would provide options deep inside contested airspace without excessive signature growth. Maritime warfare remains part of the brief. Configurations using supersonic or potentially hypersonic anti-ship weapons are being studied to counter fast, high-value naval threats in both confined and open ocean theaters. By combining these offensive options with improved stealth and sensing, Lockheed's concept aims to let the aircraft reach into areas many would assume are off-limits. Sensors directly shape how those weapons can be used. The Super Lightning concept includes a planned upgrade to the F-35's infrared capabilities by building on and extending the functions of the aircraft's existing electro-optical targeting system, EOTS, and distributed aperture system, DAS. An enhanced infrared search and track, IRSD, would widen detection range against all classes of aircraft, including stealth designs, by passively tracking their thermal signatures. Because IRSD systems do not emit energy, they allow the aircraft to search without revealing its position. For operators facing advanced adversaries with their own stealth fleets, their value lies in detecting and following targets that radar may struggle to hold. Radar upgrades are expected to focus on agility and parallel tasking. A refreshed active electronically scanned array will be able to run multiple functions at once, searching far ahead for airborne threats, mapping ground targets with precision, and intercepting electronic emissions. When paired with faster processors, these inputs can be merged with infrared and off-board sources into a single integrated battlespace picture, cutting the time needed to interpret multiple sensor feeds and reducing decision latency for the pilot or AIcopilot. Lockheed's proposal frames this in streamlined terms: greater reach through new munitions, expanded tracking via passive infrared, more flexible employment through networked targeting and retargeting. This structure underlines how the Super Lightning's upgrades would combine distinct advances into a coherent whole. Data sharing underlies much of the proposed capability. Multi-band, encrypted links hardened against jamming could connect the aircraft not only to other fighters, but also to drones, ground units, and naval forces. In practice, this means the Super Lightning could fire without turning on its own radar, by using sensor data from a surveillance aircraft, or conversely, receive targeting information to hand off to allies positioned to launch. In air-to-air engagements, it could silently push targeting tracks to partner fighters, enabling them to shoot from advantageous angles without tipping off an opponent's sensors. In such a networked role, the aircraft becomes more than a shooter. It can cue and coordinate other assets, manned or unmanned, while retaining its own strike options. This aligns with how many sixth-generation concepts envision the crewed aircraft, at the center of a connected web rather than as a solitary system carrying all weapons on board. The rationale is shaped by a competitive environment in which peer adversaries are pairing long-range sensors, robust electronic warfare, and autonomous escorts specifically to challenge stealth platforms. Systems like China's long-range IRSDs or Russia's networked surface-to-air radars are intended to close the surprise gap. For the Super Lightning to remain viable, its weapons and sensors must support operating from positions of relative safety, beyond reach of detection or engagement, or using coordinated formations to blunt those threats before they can act. Flexibility in weapons integration is also a hedge against surprise. If a potential rival introduces a new missile with marked range or seeker advantages, or a sensor that reduces stealth effectiveness, the ability to rapidly field a countermeasure matters. Lockheed's open architecture software and adaptable hardpoints are pitched as enablers for that kind of adjustment without long delays or massive retrofit work. There's a practical cost and force structure argument here for allied operators. Smaller air services cannot sustain large, specialized fleets for each role. An aircraft able to switch between air defense in one mission cycle and anti-ship strike in another compresses that requirement. With upgraded sensors, diverse weapons loadouts, and networked employment, a single type could fill multiple roles without major compromises. By bringing together contemporary weapon tests like the LRASM integration and AIM 260 development, planned enhancements to passive and active sensors, and a connectivity suite designed for contested spaces, Lockheed's Super Lightning proposal sketches a fighter that serves as part shooter, part sensor hub, and part coordinator. Its effectiveness will be measured not just in its own kills or strikes, but in the influence it can exert across the battle space through others. Realizing that vision would require sustained funding, operator buy-in, and careful management of integration risks, none of which come without hard choices. The scope of proposed changes touches nearly every mission system and some aspects of the airframe, tying development to budgets and timelines that compete with other priorities. Whether those choices make sense depends heavily on how the cost compares to alternatives and what value operators place on using a mature production line as the upgrade foundation. That question sits at the heart of the next consideration. The cost argument. Lockheed Martin frames the Super Lightning's appeal around one central proposition: that it can offer a major performance boost without the financial shock of an entirely new fighter program. The argument begins with the economics of working from an established platform. The F-35 production line is already mature, with facilities in the United States and multiple partner countries feeding a global supply chain that supports over 1,000 active jets. Procurement data for 2024 puts the flyaway cost of a new F-35A in the mid-$80 million range. Lockheed claims that by building the Super Lightning on this foundation, upgraded variants could flow down the same lines with minimal disruption, avoiding the expensive tooling changes and factory build-outs that come with a clean sheet design. This baked-in efficiency, they argue, keeps unit costs lower before a single enhancement is applied. Equally important is the sustainment network. Every current F-35 operator has invested heavily in trained maintainers, stocked parts depots, simulator facilities, and ground support infrastructure. These represent years of development and billions in program spending. A sixth-generation fighter would require re-establishing these channels from the ground up. New technical manuals, unique spares, fresh training pipelines, and possibly different basing requirements. By keeping the Super Lightning compatible with the existing logistics and maintenance schedule, Lockheed contends that operators avoid replicating sunk costs and can keep lifecycle expenses in check, alongside procurement savings. In contrast, the financial weight of an all-new program is considerable. Independent defense analysts widely estimate that the U.S. Air Force's NGAD fighters could have a per-unit flyaway price approaching or exceeding $300 million, though this figure is based on press speculation rather than any released contract data. Such numbers fold in years of design, prototyping, wind tunnel testing, subsystem development, and the high per-aircraft costs of low-rate initial production. Until production volume rises, overhead and R&D recovery inflate the sticker price. By comparison, Lockheed's stated goal for the Super Lightning is to stay well under those figures, closer to the current F-35 baseline, even after factoring in stealth refinements, AI systems, and enhanced sensors and weapons. They present this as a target for their engineers, not a fixed guarantee, and accept that outside verification would be needed before any procurement decisions. Lifecycle cost is a recurring point in debates around the F-35. Supporters note that economies of scale from thousands of units help keep fleet sustainment manageable, while critics often cite the widely discussed lifetime sustainment estimate that some analyses place above $2 trillion for the program as a whole. This number, often used in political and media commentary, is not an official final bill, but a projected sum over decades of operation. Lockheed leans on the argument that any aircraft evolved from the current F-35 would spread its support costs across that existing global fleet, avoiding the parallel sustainment burden of a separate sixth-generation type. The industrial logic is simple. Reusing the same production infrastructure and sustainment ecosystem lowers short to mid-term costs. A new clean sheet fighter demands vast upfront spending, both for R&D and for production facilities, plus a slow, expensive ramp up to efficient manufacturing. The effect is felt twice, in higher early unit costs and in the cost of building all the associated training, maintenance, and support systems from scratch. In contrast, an upgraded derivative can be built, supported, and fielded within systems that already exist, which reduces risk and compresses timelines. Lockheed also links cost efficiency directly to availability. If a matured line can switch to building Super Lightning configurations without long delays, deliveries could begin years before the first operational sixth-gen fighters appear in squadron service. The near-term value of that is clear. Capability in hand sooner, without a procurement shock that forces trade-offs elsewhere in the defense budget. There are established analogues for this logic. The US Air Force's F-15X was purchased to replace older Eagles quickly and cost-effectively, while fifth-generation and future platforms progressed. Lockheed positions the Super Lightning as similar in concept, a way to add capability without adding an entirely new type to the roster, but starting from a stealth foundation and pushing towards select sixth-generation technologies. The company underscores that reduced downtime for conversion training and compatibility with much of the existing logistic pipeline means a smoother ramp into service. Still, critics warn that the price edge could erode. Ambitious systems like directed energy weapons, major propulsion upgrades, or highly advanced autonomy packages are expensive, and integrating them could push per-unit costs closer to clean sheet competitors. Lockheed's counter is the modular acquisition approach. Operators choose the upgrade increments that fit both capability needs and available budget. This spread-out integration model avoids an all-or-nothing spend and lets programs evolve without derailing long-term fiscal plans. From an industrial-based standpoint, the pitch is not just about competitiveness in the export market. It's about keeping skilled labor, specialized tooling, and low observable manufacturing expertise active. A steady flow of upgraded F-35 orders sustains the subcontractor network and avoids the steep cost of restarting a dormant line. This aligns with the broader defense industrial policy aim of maintaining capacity to produce advanced fighters without long breaks. Partner nations also weigh total program cost beyond procurement. Weapons integration, support facilities, and software updates all factor into the long-term spend. A derivative like the Super Lightning could slot into current frameworks with targeted updates, preserving most of the existing investment in training, infrastructure, and logistics. Conversion instruction for pilots will be far shorter than a full-type rating for a completely different aircraft, further easing budget and manpower strain. Lockheed's messaging stresses that lower cost is not the same as lower capability. In their framing, the technology selected for the Super Lightning target, the mission sets where an upgrade can deliver nearly comparable operational effects to a new-build 6th-generation jet. Stealth improvements tuned to current sensor threats, AI to manage workload and enable unmanned coordination, weapons and sensors to extend engagement reach. The main financial difference comes from building on existing sunk costs in design, manufacturing, and sustainment rather than starting anew, not from deliberately holding performance back. In strategic terms, the Super Lightning concept is offered as a way to compress the performance gap without absorbing the full financial and logistical impact of changing generations. For cash-constrained operators, the prospect of buying in sooner, fielding at lower marginal cost, and keeping fleet management consistent is intended to be a compelling case. Whether that case can translate into sustained orders, however, will hinge on factors outside the factory floor. The future viability of the Super Lightning will depend on who decides to put it in their inventory and how many airframes they are willing or allowed to buy. Export market realities. In assessing the Super Lightning's prospects, the international market will be a decisive factor. The existing F-35 user base is extensive. By 2025, more than a dozen nations have invested in the aircraft, along with the training pipelines, support networks, and maintenance infrastructure that keep them operational. In principle, these customers are the most logical candidates for an upgrade. In practice, uptake will be shaped by budgets, national defense priorities, and political constraints, all of which can shift quickly. Recent examples show how varied these factors can be. Belgium's decision to expand its planned F-35 fleet illustrates that some operators are still increasing their commitment to the platform, reinforcing long-term reliance on it as their primary combat aircraft. Others have been more cautious. Canada debated for years before finalizing its purchase and ultimately reduced its numbers from early projections. The UAE withdrew from F-35 purchase negotiations entirely after disagreements over terms and technology safeguards, and Turkey was removed from the program over security concerns. Portugal, despite being a long-time NATO member, has been hesitant to commit to the F-35 at all. Each of these cases highlights how export realities extend beyond performance and price. Export control policies are a constant backdrop. The most advanced F-35 capabilities and any future Super Lightning upgrades would remain subject to US government approval. Sensitive features, whether AI mission systems, electronic warfare suites, or low observable materials, can be restricted or modified for certain buyers. Approval or denial of full capability packages will depend on strategic trust, alliance structures, and the perceived risk of technology transfer, which means not all customers will be able to buy the same aircraft. Across the current and potential customer set, three broad archetypes emerge. The first group consists of committed F-35 partners likely to adopt substantial upgrades. Nordic operators, such as Norway and Denmark, along with several NATO allies, already regard the F-35 as their only top-tier fighter and have invested heavily in supporting infrastructure. The second group is made up of budget-constrained buyers. often smaller air forces, that may prioritize cheaper alternatives over comprehensive upgrades. For these states, the lower acquisition and sustainment costs of platforms like the Gripen E or advanced F-16 variants could outweigh the benefits of Super Lightning's enhancements, especially in lower threat regions. The third archetype comprises geopolitically constrained buyers who, because of security sensitivities, are unlikely to receive unrestricted access to the full upgrade suite. Here, the UAE's abortive procurement effort and Turkey's exclusion serve as clear precedents. There are also strong regional drivers. In the Pacific, Japan and South Korea face rapid modernization among potential adversaries, including the introduction of new fighters and long-range strike systems. Both are already invested in the F-35 and have the infrastructure to support it, making an upgrade path attractive if it adds relevant capabilities ahead of next-generation timelines. In Eastern Europe, Russian activity has reinforced the desire for more survivable, networked combat aircraft able to integrate with NATO's intelligence and targeting networks. Middle Eastern operators contend with expanding air defense threats and increasingly capable regional air forces, making improvements in stealth, range, and weapons integration a potential deterrent benefit. By contrast, air services in parts of Latin America or Southeast Asia may see the baseline F-35 or even earlier generation aircraft as sufficient given budget constraints and less acute threats. Cheaper non-stealth types will continue to compete for sales where technical overmatch is deemed unnecessary. While they cannot match the Super Lightning's low observability or data fusion capabilities, their affordability, easier maintenance, and lower political profile can make them attractive in lower-risk environments. Even within the stealth category, future export-oriented fighters from European or other allied programs could draw interest if they arrive with fewer U.S. imposed restrictions. Timing adds another dimension. Sixth-generation fighters from the US and allied programs like GCAP and FCAS are unlikely to be widely exportable before the mid-2030. This creates a window, potentially a decade, in which Super Lightning might stand as the most advanced Western combat aircraft available for sale. Countries unwilling to wait for next-gen options could see it as their only viable path to narrowing capability gaps in the near term. Conversely, those confident they can wait may prefer to reserve funding for a complete generational leap. Lockheed's proposed modular approach could help reach diverse buyers. Operators could select only the most relevant elements, such as stealth refinements and sensor upgrades, while deferring costlier features like full autonomy or advanced directed energy weapons. This flexibility could make the upgrade accessible to a wider range of budgets and threat environments. However, that same flexibility requires managing multiple configurations in production and sustainment, while maintaining enough commonality to preserve interoperability and cost-sharing benefits. Political alignment will remain as decisive as economic and operational calculus. States firmly embedded in U.S.-led defense networks will find it easier to secure approval for the highest capability packages. Those outside such frameworks, or pursuing more independent defense policies, may face reduced configurations or outright denials. Changing diplomatic relationships can also reorder the export landscape mid-program, as past program history has shown. For Lockheed, these market realities carry direct implications for the Super Lightning's economic viability. Widespread uptake would sustain production volumes, keep per-unit costs competitive, and maintain the shared sustainment structure essential to the F-35's existing global model. A narrower customer base risks driving costs upward and eroding the financial advantage at the heart of the upgrade pitch. The Super Lightning's fortunes in the export arena will ultimately determine whether it achieves the production scale needed to make its business case work. That production scale is not just a corporate goal. It is the mechanism that holds down unit costs, supports interoperability, and sustains allied fleets during the period before true sixth-generation aircraft become widely available. How the next set of procurement choices fall across these varied customers will shape not only the fate of this proposed upgrade, but what Allied air power looks like in the decade ahead. Those choices, however, connect to a broader strategic question. What happens if reliance on such an upgrade changes the pace at which new generation fighters arrive? That question carries its own risks, and its answer may determine whether near-term economy translates into long-term strength. Risks of delaying sixth-gen entry. Delaying the introduction of a true sixth-generation platform carries strategic risks that go beyond the timeline of any single program. If that delay coincides with the arrival of rival designs reaching operational status, the resulting capability gap could be difficult to close. In an era where generational shifts redefine not just the aircraft themselves, but the way entire air campaigns are executed, holding onto upgraded fifth-generation designs as the primary frontline option for too long could give competitors time to field systems tailored to exploit their known limits. Program timelines add weight to that concern. The US Air Force's NGAD effort, the UK, Italy, Japan Global Combat Air Program, and Europe's Future Combat Air System all currently aim for initial operational capability in the mid-2030s. If those targets hold, there is a very real possibility that multiple Allied and rival sixth-generation fighters could enter service before the US fields its own in meaningful numbers, especially if investment and focus are diverted toward extending the life of existing platforms. In that kind of environment, the first mover stands to set the pace for capability development for years afterward. Potential adversaries are also advancing. Reports and analyst assessments suggest that China is accelerating J-20 production while continuing parallel research into what some sources refer to as a notional J-36. While firm details on the latter remain scarce, open reporting links its design studies to capabilities often associated with sixth-generation aircraft. Adaptive cycle engines for extended range, refined stealth shaping to address emerging radar threats, and integrated control of unmanned escorts. If even some of those features move from prototype into service ahead of US timelines, the Indo-Pacific's air balance could shift toward forces with longer reach, broader sensor coverage, and more flexibility in contested environments. European efforts add another competitive axis. FCAS partners, France, Germany, and Spain, plan to combine a crewed fighter, loyal wingmen, and a persistent combat cloud in their mid-2030 system. GCAP's stated schedule is similar, but with an explicit push to expedite development. If these programs meet or approach their targets, export-capable variants could be available abroad before US sixth-generation production moves past low-rate quantities. That could make Allied air forces more likely to standardize on non-US sixth-generation designs, potentially reducing American influence over shared doctrine and interoperability standards in coalition operations. What losing time looks like in practice is illustrated by a hypothetical but plausible scenario. In a high-threat maritime theater, a formation of fully integrated sixth-generation fighters arrives accompanied by multiple loyal wingmen, each carrying specialized sensors and weapons. While the crewed aircraft remain outside the densest air defense zones, the unmanned escorts advance to map threats, jam sensors, and launch long-range standoff weapons, all coordinated in real time through a secure, distributed network. An upgraded fifth-generation jet operating alone, even with stealth refinements and AI-assisted systems, could struggle to match that distributed reach and layered defense-offense capability. The gap is not only technological, but operational, as the sixth-generation package fights as a network from the outset. This risk of compounding disadvantage grows once a new generation starts iterating in service. Historically, first-generation production models are only a starting point. Within a few years, software updates, refined mission systems, and new munitions push performance well beyond the launch configuration. If competitors can add successive increments to an already superior baseline, while US forces remain bound by the design limits of an older airframe, catch-up becomes exponentially harder. Training and tactics also evolve around what is in service. If frontline US and allied squadrons continue to operate within a fifth-generation performance envelope, their training cycles and doctrine will reinforce the strengths and limitations of that generation. The eventual arrival of a sixth-generation aircraft would require a disruptive shift in pilot training, mission planning, and maintenance support, while facing adversaries who by then may have a decade of operational experience with their own advanced systems. There are industrial implications, too. Postponing a full sixth-generation production risks losing momentum in areas like advanced thermal management, broadband low observable materials, and integration processes for manned-unmanned teaming hardware. Without steady work, highly specialized suppliers and skill sets can migrate to other sectors. Reconstituting that capability later can be more expensive and time-consuming than sustaining it continuously through an active program. Budgetary logic for delay can be self-defeating. Allocating funds to extend and upgrade the F-35 into a Super Lightning configuration may appear to save money in the near term, but the bill for a sixth-generation fleet does not shrink. It is merely deferred. When the moment inevitably comes to launch full-scale production of a new type, it will have to compete for resources against the cost of keeping an aging fleet both serviceable and relevant against advancing threats. That dynamic could slow new procurement rates, leaving the gap unclosed for even longer. Operationally, there are hard limits to what any retrofit can achieve. Rear aspect stealth tuning, advanced autonomy functions, and sensor overhauls improve survivability and lethality, but cannot replicate the advantages of an airframe designed from inception for multi-spectral stealth, extreme sensor integration, and high-efficiency propulsion matched to unmanned team operations. In a world where peer competitors field such designs, those differences can define the terms of engagement. Allied perceptions add another layer to the strategic picture. If partner air forces move first into sixth-generation service, it could subtly shift coalition dynamics. The ability to share equally in the most demanding mission sets depends on fielding comparable capabilities. If US fighters are viewed as half a generation behind in key aspects, even temporarily, the influence they exert in shaping joint operations could diminish. The aggregate risk extends beyond individual aircraft match-ups. It is about who sets the benchmark for air combat capability, who dictates the pace of adaptation, and whose concepts become the default for training, procurement, and deployment planning. Each year spent without a mature sixth-generation capability is a year in which others can refine both the hardware and the doctrine to employ it effectively. Time lost at the front end is rarely recovered once capability gaps open across multiple domains. That said, the Super Lightning's potential role as a stopgap should not be dismissed. For some militaries, it could provide an affordable way to increase capability in the short term, maintaining deterrence and operational effectiveness while buying time for more ambitious programs to reach production. This hedging approach, introducing incremental advances now while keeping pressure on sixth-generation schedules, may be the most politically and financially viable path for certain operators. Still, balancing near-term upgrades against long-term generational change is an exercise in managing risk, not eliminating it. Decisions made in the coming years will shape not only future air combat capabilities, but also the ability to maintain strategic continuity in design, production, and sustainment. That continuity is its own form of readiness, one that depends heavily on how industrial capacity is maintained between generational shifts. Industrial base and strategic continuity. Lockheed Martin frames the Super Lightning not only as an aircraft upgrade, but as a means to keep a rare and fragile industrial ecosystem in motion. Advanced combat aircraft production depends on a workforce spread across highly specialized disciplines: composite materials experts, precision machinists, flight control software engineers, propulsion integration teams, each of whom maintains skill at the highest level through constant application. Interrupt that pipeline for too long, and those skills erode. Key personnel migrate to other sectors, and rebuilding that capability takes years. In its April 2025 investor call, CEO Jim Taiclet pointed to the thousands of engineers engaged in design, integration, and testing on current programs as a core national asset in themselves. Without a funded and active production program, that asset risks dispersal just when the next leap in capability is needed. The company's position in the tactical fighter space shows the stakes. Lockheed dominates current fifth-generation production through the F-35, yet stands outside the prime contractor role for both NGAD and F/the Roman 20. That leaves an opening in the mid-2030, where its largest combat aircraft contracts could taper without a comparable follow-on, creating a gap in design and production flow. In early 2025, Lockheed disclosed over $1.9 billion in charges tied to undisclosed classified programs, an indicator that not every advanced effort results in sustained production. Without something like the Super Lightning to keep production humming, its ability to bring a complete state-of-the-art fighter from design to rollout on short notice could weaken. That erosion is not just a corporate concern. It affects the balance of the entire US fighter building base, which relies on having multiple, fully capable primes. The US primes, Lockheed Martin, Boeing, and Northrop Grumman, each sustain their own design cultures, proprietary processes, and supplier bases. Falling behind for even one generation risks losing not only market share, but the tacit knowledge that comes from hands-on integration of fundamental shifts in propulsion, networking, and multi-spectral stealth. Those are not skills that can be instantly reconstituted with new hires. They build over years of iterative problem-solving on real aircraft programs. Past industry cycles have shown what happens when lines close for extended periods. Suppliers disperse into other markets, engineers with decades of experience retire or change industries, and the effort to reassemble a functioning team slows the pace of any future ramp-up. The supply chain dimension is equally critical. Their F-35 program depends on a globally distributed network of subcontractors building stealth-qualified components, advanced electronics, and high-tolerance structures. Many of these companies are embedded in local economies in the US, Europe, and Asia. A sudden drop in orders can push them into commercial aerospace or unrelated defense work. Once they pivot, drawing them back into low observable fighter production requires new contracting, requalification, and often reinvestment in tooling. A continuous upgrade program like the Super Lightning would maintain steady demand, keeping those suppliers in practice and ready for whatever the next generation designs require. From a strategic planning perspective, an active production line is a form of latent surge capacity. If an urgent threat emerged, having multiple primes with active fighter programs compresses the time from concept approval to operational aircraft. Without that, the workload concentrates in fewer hands, increasing bottlenecks and stretching timelines. That time loss in a crisis could leave the US and its allies at a disadvantage against a peer that has kept its production warm. For the workforce itself, live upgrade projects sustain proficiency in ways pure research cannot. Integrating a new radar with a stealth airframe, adapting flight control systems for autonomous teaming, or expanding thermal management for advanced weapons each requires the same high-stakes, cross-discipline trade-offs as a clean sheet program. This is the kind of integration practice the Super Lightning could provide, ensuring key engineering teams remain fluent in applying emerging technology to operational platforms, not just demonstrating it in isolated testbeds. The incentives extend beyond domestic readiness. Many allies have invested heavily in F-35 specific sustainment networks, training pipelines for pilots and ground crews, simulator infrastructure, maintenance tooling, and parts distribution hubs. Keeping the production pipeline open supports their readiness as much as Lockheed's. A warm line ensures parts commonality, consistent upgrade flows, and a synchronized service baseline across allied fleets. If the US industrial base contracts and that pipeline cools, the effects reach every partner who depends on timely deliveries and compatible configurations. When multiple capable manufacturers remain active, the benefits go both ways. Government buyers have alternatives if one program hits technical trouble, and the competitive pressure helps control costs while encouraging innovation. Reduce that competition, and the risk rises that costs drift upward and advances slow. In a sector where the jump from one generation to the next can define operational advantage for decades, those slips are difficult to reverse. The export angle deepens the policy relevance. The F-35's success abroad in numbers, reach, and interoperability ties many US allies into a common security architecture. If Lockheed were to lose ground as a fighter producer, those partner fleets could be drawn toward other suppliers' platforms in the next cycle. That would weaken both the industrial and operational integration that underpins coalition air power. The Super Lightning, as framed by Lockheed, is presented not only as a way to hold market share, but to maintain that shared ecosystem through the transition to sixth-generation capabilities. Funding decisions on interim upgrades often mix operational necessity with industrial policy. Even if a Super Lightning variant's performance gain could be partially matched by other options, its value as a bridge program lies in reducing the cold start penalty when a new aircraft is finally green-lit. The alternative, allowing teams and facilities to go idle, forces a slow rebuild that international competitors may exploit. There's also a technology pacing benefit. Keeping the design, production, and test teams engaged in physical integration keeps their skills aligned with the state of the art. Materials science, avionics, communication protocols all evolve quickly. Teams working continuously on actual aircraft incorporate those changes as they occur, rather than trying to relearn them in compressed timelines years later. This makes the transition to whatever follows, sixth generation or beyond, faster and less risky. For defense planners, industrial vitality is inseparable from force modernization. A combat-ready fleet supported by a stagnant production base is inflexible. The reverse, a healthy industrial base with no relevant current platform, limits immediate options. The policy calculus for mid-life upgrades or bridging programs therefore spans beyond platform performance metrics. It considers whether those programs keep the national design and manufacturing apparatus in fighting condition to respond rapidly when the strategic environment changes. Lockheed frames this proposed path as an opportunity to maintain full-spectrum fighter design skills while weathering a generational handoff. In this light, the Super Lightning is both an operational tool and an insurance policy. It keeps the workforce, supply chain, and integration expertise aligned to current demands, while buying time for the deeper leap of a new-build sixth-generation platform. With those industrial and strategic factors in mind, the remaining question shifts from what can be built to what should be prioritized next, and how that choice defines the balance between near-term capability and the momentum needed for the next generational leap. At its core, the decision comes down to two paths: invest now in a deep F-35 upgrade, or channel resources into fielding a clean-sheet sixth-generation fighter. The first offers faster delivery and lower upfront cost. The second demands far more time and funding, but promises capabilities a retrofit cannot fully replicate. Both approaches are already moving forward in major air forces, and the short to mid-term choices made now will shape combat air power into the 2030s. Which risk would you accept? Pay more now for a next-gen platform, or upgrade the fleet and buy time? Tell us in the comments.